Okay, let's see. So I'll give it another minute or so here in case anyone wants to jump in the chat while I get things set up quick. All right. Oh, let's see. Oh, oops, there we go. Ooh, okay, just got a ooh, sweet. 1 second. Let me just check this out quick. Wanted to make sure we didn't have any questions before we started. I did just pick up a question. All right. An example like 4A or 4B tonight on the homework. Yeah, okay. Let me pull that up and see if we can do something to that effect. Okay. Yeah, so enough just silence on the mic there. Let's get into it today. So today we're going to talk a bit about the properties of complex numbers, figure out some ways to do a lot of things a lot easier. Um, so let's start out though before we get into this with a quick example. So here, let's just scroll over to the side quick and try something out. So we got a request to do problems like 4A and 4B, basic stuff with calculating or simplifying roots of complex numbers. So idea being square root, say, of z. How do I find this? Um, well, we last time found a nice little formula. So here, let me give myself a little bit more room there and get out of this. So here, just to recall, just to start things off, recall. Um, so let's let, um, oh, we'll say, how should I write this? Let's let z squared be equal to w, um, where, actually, let's even make this easier. Let's just say this exactly how they say it in your book, so I don't add any additional confusion. Let me pull it up quick and make sure I've got it exactly the same way. Um, so this is the big ugly formula we talked about last time. I'll just write it in the simplest, most straightforward, nice way we could do it, which is to say, oh gosh, I guess I could have done that. Oops. Here. All right, off to a rough start right there. All right, let's get back to it. All right, so the square root, if you recall, of a plus bi, um, this is going to be given by plus or minus alpha plus mu beta I, um, where alpha is given by the square root of a plus the square root of a squared plus b squared all over 2. Beta is equal to the square root of minus a plus the square root of a squared plus b squared over 2. And I should be clear, this square root sign does the whole thing right there. Drawn a little bit too quick on this tablet. And then this little mu right here is given by just to kind of put that right there. This is going to be 1 when b is greater than or equal to 0, and -1, let's put my little hats on the one there, when b is less than 0. Yeah? So problems 4, A, B, and C on the homework involved computing square roots of complex numbers. Some of them were trickier where they had square roots of square roots. This just means you apply the process twice. But let's try something straightforward. Let's say, let's make your lives easy. You have to do this in part of problem 4A. So let's compute square root, say, of I. So we'll do an example here. Okay, so square root of I, this is really the square root of 0 plus 1 times I, to put it in the form of a plus bi, right? Okay, so if we're going to do that, then, this should go all the way over that, if we go through and we actually compute some stuff out, this will be plus or minus the alpha term. So the alpha term is given by one big square root here, so it's going to be a, that's 0, plus square root of a squared, so that's 0 squared, plus b squared, that's 1 squared. We'll put that all in that square root, and then it's going to be over 2, and so I'll put all this in there. That's the alpha term. And then I'll go plus mu. Remember, mu is going to be 1 if b is greater than or equal to 0, and -1 if b is less than 0. So since b is greater than or equal to 0, that's going to just be a 1. 1 times, and now we'll do the beta term, which is exactly the same as the alpha term, except for the fact that instead of a, it starts with a minus a. So this is going to be minus 0, which is still 0. Then we throw the square root in here, 0 squared plus 1 squared, a squared plus b squared, all over 2. I should make that a little cleaner. And that's going to be what the answer is if we want to go through and actually solve this out. I'll get plus or minus, well, let's go through, I'll get 1 over 2, so this is all in a square root of 1 over 2, plus, I forgot to put, wow, look at that. Be careful when you're going fast like this, not to make a dumb mistake, which is to forget your I right here. And that I is outside of this radical, just to be clear. So if I want to be very precise in how I write this, I could put parentheses around here and then put a parenthesis at the end. That makes it look a little bit messy right there, but we'll write it out a little bit cleaner. So we got this plus or minus right here, and I'll put a parenthesis there just to keep everything clear. And so we got 0 squared, or 0 plus square root of 0 squared plus 1 squared, so that's just going to be 1/2 in there, in the side of that square root. Then I got the 1, and then up here we've got this guy. I want to make sure I didn't make that mistake forgetting the I up here. Yep, no, I got it right there. Okay, good. So we do the same thing. We're going to get the same thing over here. Square root 1/2 I. And if we want to go through and maybe make this a little bit nicer, we could say plus or minus root 2 over 2 plus root 2 over 2 I. And that's how you do something basic like that. If you had something a little bit more complicated, you would have different things other than A's and B's. If you have, say, a square root involving a square root of I, you'd do the innermost term first, and then you'd get your answer and you'd plug it in, and you'd continue going. The number of solutions you get should be 2 to the number of square roots there are. So if you, say, have 1 square root involved, like you have right here, so square root of I, you'll get 2 solutions. If you're looking, say, at square root, as you'll do in your homework, say at 1 plus the square root of I, then you should get 4 solutions. So this will have 4 solutions. While this guy only has 2. So that's just an easy heuristic. All that stuff aside here, let's get that out of the way. We can probably jump into today's stuff. Let's see. Where did I put that? Layers. Okay, so I'll throw that layer away. And I'll get rid of this. Okay, and let's start talking about some properties of complex numbers. So, the real gist, and let me make sure I'm going to start at the right place. All right, cool. The real gist of what we're going to talk about today is a much easier way to do what we just did than that horrific formula. No one likes that formula. It's ugly. It's just god awful. It's something that nobody particularly enjoys, and for that reason, we're gonna never hopefully have to deal with it again. So just to make our lives easy, we can do a lot of this without having to write things down, and I think I can just explain it fairly well, and we'll save ourselves a lot of hassle. So we'll start out just by looking at a regular old plane, the regular old complex plane C right here. So this guy is going to be the complex plane, so that means that this is the real axis and the imaginary axis. All right, now if we say pick a complex number, let's call this AB, right? So it's like a point right here in space, and associated to it, we can look at, say, basically a vector, right? So I am being somewhat pedantic here, whether we want to consider this a vector versus points, etc., etc. But there's something right here, and we often write this instead of as a pair AB, we write this as instead A plus BI, whichever you prefer to write it as. It doesn't really make any difference to me. For convenience, we'll just write it as A plus BI for the moment, and just keep everything in one notation. So A plus BI right here. And naturally that means we have a vector associated to this right here, or it is a vector if you want to look at it like that, with A on the real axis and B over here on the imaginary axis. So you guys have all taken Calculus 3, I believe, so you're all familiar with the idea of different coordinate systems. If you've taken linear algebra, you've probably also seen different coordinate systems. Nothing too fancy. But basically, to represent this point, and this is what I'm getting at when I'm talking about, we can do it as a pair or A plus BI. That's written in terms of a basis given by the real part. You can think of this as like 1, 0, and the imaginary part, which is something like 0, 1. But there are plenty of other bases, right? And we're basically just suppressing this little real part. That secretly is hidden right over here, and then this piece right here is the I, if you want to think of it like that. We're basically just writing things in terms of basis, but there's more than one basis for R2. That is, we can write C in terms of A plus BI, but we can also write it in other ways. Here's one good way that will make things particularly convenient for us, and we're going to really, really get some mileage out of this. So let's get a slightly different color right here. Namely, this guy here has a certain length to it, right? Let's call this R. And then if we looked at the angle right here from the real axis, we could call that, say, theta. And knowing the angle, theta, and the radius would certainly specify the point just as well as knowing the xy coordinates. So we could also look at this as r theta instead of AB. Get what I'm saying? A plus BI or r theta? Fair enough. We could look at it both ways. And so looking at the so-called polar representation of a complex number, that is in terms of r's and thetas, will be very, very useful for us. I believe everyone has encountered this many a time when dealing with like the method of cylindrical shells and all that sort of stuff in Calc 3 or Calc 2 even. But nothing fancier than that is going on here. The whole idea is that we've got a triangle hidden in here, and this gives us some nice basic stuff. Namely, we know that, so if you have a triangle of so here, just to refresh your memory in case anyone has forgotten, you got a nice right triangle right here, so that's a right angle. If this is length 1, and that's an angle of theta. Then you remember SOHCAHTOA, sine opposite over hypotenuse, right? So this would be sine theta. This is cosine theta. If you just scaled everything up and made it bigger, if this was an r instead of a 1, if you stretched it out, so if this was an r instead of a 1, then of course we would just be dilating the rest of the things in the same way. Why isn't this going back? There we go. So if that's an r, then we'll just get an r and an r. So here is basically what we've got. We've got, oh, look, A is r cosine of theta, and B is r sine of theta. Oh, look at that. So realistically, if you have a complex number z, you can write this as a plus bi, but you can also write it as r cosine theta plus r sine theta times I. Oh, hey, how about that? And normally people like to write this as r cosine theta plus I sine theta. And some people even write this as RCIS, cosine I sine theta. We won't use that notation here because it's, I don't know, we don't need to introduce new functions or anything weird here. But you can, if you like doing that. I think it does save you some time. But this little trick right here, this looking at it as a polar, in polar coordinates is very useful. It's just a little bit of notation. When we talk about the modulus or absolute value of z, which we'll denote by these little bars, it's really just the measure of the length of a complex number. So if a plus bi right here is the complex number z, then the modulus of z will be r. Okay, and we'll also talk about the argument, argz, which we'll just take to be this angle theta. So there are two functions, mod or absolute value and arg. The arg of a complex number is the angle theta, and what we want to pick for arg, whether we look at, say, this angle theta or we look at some other angle, maybe this one right here, is perfectly valid as well. That would be minus 2 pi plus theta. That is a perfectly reasonable thing. We could define argz to be as well, but we'll have to pick something to get a unique representation, and so which we choose is a little bit up to us here, and this will give us some nice things. So this is absolute value and argument, easy enough, and using these guys we'll be able to get some nice tricks that will let us totally avoid the silly stuff that we had to do last time with things like calculating square roots of complex numbers. We won't have to do all of that garbage anymore. We can do this all very fast. On your homework, you should still do it the other way, just to do it once, see it, you know. Make sure you understand how nice it is to have these other representations of a complex number. But for now, we'll just we'll proceed to go on and find the best way to avoid having to do any of that malarkey anymore. So argument and modulus, great stuff. I think since while we're talking about it, it is worth mentioning that when we pick what the angle theta should be, that is whether we pick, oh, here, I'll just go back up to here and throw a different color at us. Maybe I'll throw like a nice like light, or I'll do dark blue. How about that? Whether I pick this one or if I pick, say, all the way around and then back, so theta plus 2 pi. What I want to pick for my value here, whether I pick that theta or this theta, this is called choosing a branch of the argument. We'll get into this a little bit later in terms of the branches of certain complex valued functions on C, but in particular, we'll think of it like this. If you're just picking whether you're in, like, say, 0 to 2 pi or minus pi to pi, or and so on and so on. So this is basically just choosing n for theta plus 2 pi n for such that n is an integer, right? So this is the case. Like arg z should at least be in here, and then which choice of n. This is choosing a branch, we'll say. So when we have these kinds of ambiguities, just this is not like a formal definition right here or anything like that, but just to get you thinking in this mindset to start with, when we have these ambiguities where we could choose multiple things, this will normally correspond to choosing a branch of something. And the intuition here being that like it could go off in a couple of different directions, and so choosing one of those paths is like choosing a branch on like the tree from which the general function grows or something. So that's a little bit of a notation, but or that's a little bit of intuition for something that we'll come across in a little bit later in the class. But for right now, let's just keep going. So one thing that's nice about looking at a complex number z, here we'll write this. One thing that's nice about looking at a complex number z in terms of this polar representation of r cosine theta plus I sine theta. One of the nice things about looking at this is that if we have, say, let's do z1, and I'll put ones on everything, and let's look at z2. This will make it really clear what's actually going on when you multiply complex numbers together. So cosine theta 2 plus I sine theta 2. When you multiply things, let's just actually go through and do it. So z1, z2, we'll get, well, let's just write it out. I'll save myself a little bit of time. That was probably not the right thing to do. Crap, whatever. Okay, I must have my hotkeys configured wrong. So r1 cosine theta 1 plus I, terrible I right there, plus I sine theta 1. Let's just go through and write it out. Times r2 cosine theta 2 plus I sine theta 2. All right, so if we're going to go through and we're actually going to multiply everything out, it's not too bad. Well, we'll just get r1, r2, and then we'll get, well, cosine theta 1 times cosine theta 2 plus cosine theta 1. I'll put the I up front. I sine theta 2 plus I cosine theta 2, I sine theta 1, and then just to go a little bit further, we'll get minus sine theta 1 sine theta 2. And here, I'll zoom out a tiny bit, make that a little bit easier to see all at once. And if we go through and we use a little formula from trigonometry, we'll actually be able to write this out pretty well. So notice this is r1, r2, cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, plus I times cosine theta 1, sine theta 2, cosine theta 2, sine theta 1. This is an old identity from, oops, that was a terrible line right there, parenthesis. This is an old identity from trigonometry, if you might recall it. What is this equal to right here? Cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. Well, that is just, if you don't recall, this might be a good place to take a moment to go refresh your memory. This is just cosine of theta 1 plus theta 2. And I won't go through and prove that right now because it's not really the point of what's going on here. But I encourage you to take a second to go through and actually do that. And the second piece right here, cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. This is just sine theta 1 plus theta 2. Oh, whoa. What? Look at this. This is cool. Okay, so we actually have a really good way to interpret a complex number under multiplication. So here, let me rewrite this really quick so we can see it when I scroll down here. Z1, Z2, it's just got the product of their lengths, and then an angle given by theta 1 plus theta 2. Oh, hey, look. So arg Z1, Z2 is just equal to, well, hey, theta 1 plus theta 2. But wait, that's equal to arg Z1 plus arg Z2. Oh, wow. And what is the modulus of Z1, Z2? Well, that's just equal to, oh, look, it's the product of the moduli. So R1, R2, which is just equal to modulus Z1, modulus Z2. So you're just multiplying their lengths and then adding their angles. That's pretty cool. Okay, so let's kind of just visualize this really quick. If I want to just give myself a little bit of a plane here. Let me just do that. So let me give myself a copy of C here real quick. So this will be C. I'll just have usual imaginary and real axes, right? I should make that a capital. Real and imaginary. Okay, good stuff. And say I'll take one. Say this is Z1, right? Then this would be theta 1. And this would be R1. The length right there, right? Okay, then if I have, say, Z2, I'll just do this guy like this. Or here, I'll even make this one, let's say I'll make this one half as long, right? Let's make this let's call this Z2. Then this angle right here will be theta 2, and this will be R2. And when I multiply them together, all I'm doing is I'm adding theta 1 to theta 2 in terms of angles. That is, I'm taking this little angle and I'm going that much further past. And maybe I'm a little bit off here on how this actually looks. But let's say it like if you put this little guy right there, right? Here, I'll even do it in the same color, just to make it super clear what's going on. That little guy. All right, then this is going to be the right angle for how long this thing is. And now multiplying the lengths together, let's suppose that R2 is like 1 and R1, or let's say that R2 is like a half of R1, right? Then when we multiply them together, or I don't know, let's just, let's do something like this. Let's say, well, let's suppose R2 is 1 and, or R1, let's make it easier. Let's make R1 be 2 and R2 be, or here, let's just do this. Let's make our lives, let's make this illustrative at least. Sorry for my indecision right there. Let's say that R1 is given by 3, right? Let's suppose that R2 is 2, just for convenience, right? Because we have to pick something. So then if you multiply them together to get this angle, or I mean to get this length right here, how long this orange guy is, that'll be R1, R2 is 6. So there you go. And then the angle, this angle right here, is just theta 1 plus theta 2. And this thing right here is Z1, Z2. So when you multiply two complex numbers, you multiply their lengths and add their arguments. So multiply the moduli, add the arguments, and then you get the product. So it's got a very geometric description. It makes sense what's going on. And in particular, this will make certain things really easy to deal with. For example, finding square roots. That is something where you are doing some multiplication and figuring things out like that. So, and here, I'll just, I'm going to skip over a section in the book for the moment. But let's think it through and try to look at, say, the roots of unity, of one, let's say. Let me pull this down really quick. So here I'll put add a new layer. I'll take this old layer off. All right. So if we wanted, say, to I don't want to actually keep that over there. So let's say we want to figure out what's going on with things on the unit circle. So I'll just grab a copy of C really quick, and I'll make the unit circle. In case I actually don't think I have used this term, but in case anyone is unfamiliar, it's a very common term. The unit circle is the circle of radius 1. Since we're in R2, it's just a circle in R2, all the points in R2 that have distance 1 from the origin. And in our case, this will just be something like this, right? So if I'll make this pretty easy to look at, I think, if I do this. So let's let this be the unit circle. So that means that this distance right here is 1, right? Okay, so that's a distance of 1, and we're sitting here in C. I should write this all in white just to make it clear. This is the imaginary axis, this is the real axis, and just to not make things cluttered, I'll get rid of that 1 right here, since we won't need to actually talk about it. But notice that if we're sitting here on the unit circle and I take some point here, let's call this Z, well, then Z will be given by, well, it's R cosine theta plus I sine theta, for the theta corresponding to this point. And in our case, that will just be this theta. And R here is 1, right? If we're on the unit circle. So if we say square Z, if we go Z squared, what are we going to get? Well, here, I'll even write this off to the side so we don't get too cluttered. Well, Z squared, I'm just going to multiply the R's, right? R times R, so R squared, cosine of theta plus theta, plus I sine theta plus theta. And I'll put that all in parentheses. That's just what we were just looking at. Okay, cool. Well, what is this? Well, if I square R, R's 1. It's the same thing. This is just cosine of 2 theta plus I sine 2 theta. Oh, how about that? That is kind of easy. Okay, so I just go twice as far. So I just do yet another one of these little thetas over. And then, here, I'll even do this in a different color just to make it clear. Just another theta over. And then I just take and I do this. Hey, what the heck? Now I've got Z squared. Oh, okay, and if I keep going, well, I'll just keep making little slices of the pie, so to speak, that have the same angle thereabout, right? And I get so on and so on and so on. I'm probably not doing this that exactly, right? But you get, I hope, the picture of what this starts to look like. I am just rotating around slowly. I'm going, okay, Z to the third, Z to the fourth, Z to the fifth. If this was a piece of pizza, we are just counting the cuts we make, right? The powers are just counting cuts. Oh, that's kind of cool. z to the 8th, and so on, right? I should maybe have done less of these. But basically, we're just taking this point and we're going over, and we're going over, and we're just rotating around. So that's kind of nice. Now, when we're taking things that don't have modulus 1, instead of just rotating like this, we'll actually also be stretching. If r is greater than 1, it will be stretching outwards. If it is less than 1, it won't be. It'll be spiraling inwards. So that would be, instead of like going like this, if we were off the unit circle, we'd instead start with something here and then go to like here and then go to like here and then so on and be like flying out, right? You see what I'm saying? Well, if we had something less than 1, we would go here and then we'd get getting shorter and then we'd be getting shorter and then shorter and shorter and shorter and shorter and shorter and shorter and spiraling in, right? So this is kind of cool. You can kind of see what the imaginary part does, namely if you have an imaginary part to your complex number, right? If it's not just purely real lying on the real axis, then that imaginary part under multiplication basically is the piece that's rotating you. The real part just decides to some extent how long things are going to be, right? If it's a purely real term, then it just scales. The theta is 0. If you add 0 to a different angle, it's not going to do anything. So things on the real axis just scale. But if you're at all off the real axis, then you're going to be doing some rotating. It's kind of cool. All right, that makes sense. So, and here's where you can start to see the beginnings of hints of number theory here. Stuff to do with the primes. Notice that if I have set this up nicely, I will circle all the way around just back to where I started. Namely, well, actually here, let's take a moment before I talk about that. This is where you can start to see the beginnings of number theory and some of the ways you can use complex analysis to investigate the primes, and people do, and it's very fruitful. And I think my son is fussing upstairs a little bit. How's he doing? Huh. Poor little guy. Must be having a diaper change. Anyways, hopefully that is not too annoying on the mic. All right, let's keep going. Hard to think with a baby crying. Let's see. Anyways, let's get back to it. So we'll talk about this in a moment, but first we should talk about roots of unity. That will make it a little bit clearer of what's going on. So when we're on the unit circle, this sort of thing starts to happen. And when we're looking at the square roots, say, of 1, or the 4th roots, the 5th roots, 6th roots, 7th roots, what have you, what we're looking at is we're looking at things that when you move around the circle in this way some number of times, you get back to a very special point, namely 1. And so let's start out by looking at square roots for the real number 1. And I'll just redraw this plane really fast just to make our lives easy. Keep everything uniform. Okay, so if we're looking at the very important point, let's just say that this is 1. Notice you could, if we're looking at things that you can square to get 1, you can take -1 times -1 and you can get 1, right? That is, I can look at this guy over here, -1. And if I take this this theta associated with it and I square -1, well, we already know that because we're on the unit circle, we're just going to stay on it. And so if I keep going, notice I'll get back to 1, right? This would be theta once more. This would be theta plus theta, so 2 theta, right? Okay, so if I double it, I get back to 1. Now, if I say took something, so I went like 1/3 of the way, then this guy here, another theta, right? Okay, this guy would be another like theta. Let's call this theta 2. I should put a little 1 on there, right? Theta 2. if I'm up to this, right? This would be some other thing, z. If I've done this nicely, then I should be able to go a little bit further and do like a second theta and get to z squared, right? A second theta 2, right? And then I should be able to go again and get back to 1. Oh, look. Hey, how about that? So what I'm trying to kind of write here is that I've got this is minus 1 squared, or in this case, this will be z to the third, right? Z cubed, z to the third. If I've chosen this z right, then I should go a third of the way, and then another third of the way, and another third of the way back. Hey, the roots of 1, the third root of 1, is just splitting the circle into 3 pieces, right? That's how we're getting it. We're just slicing the pie in a nice way. Namely, we'll get back, to there. We've got our 3 little cuts along these pink lines here, splitting the circle into 3 chunks. If I drew this a little bit nicer, it should be very clear that they are equal sized, right? No one would be mad if we cut this pizza up like this. Okay, cool. Same thing should hold for 4th and 5th and 6th and 7th and so on. All the different roots of 1. In fact, 1 has, 900th roots, 500 billion and 371th roots, just from splitting up the circle into that many little slices. Okay, so we should be starting to see a pattern for how to determine the roots of, say, something like 1. And notice, since if we're doing something, say, other than 1, we're probably really just doing the same thing, but just kind of rotating or scaling our picture in or out a little bit. This should really be enough to get to a general formula. And in fact, we'll be able to do this. So let's just get to a very famous result. This is called de Moivre's formula, and I will really quickly bring this over from the textbook in its original form. So I'm gonna go back here. I'll paste it in, and I will move it around really quick just to get to where we want to be. All right, good enough. Add another paint layer really quick. All right, there we go. Okay, cool. So now that we're back to it, here is de Moivre's formula. De Moivre. Maybe I'm pronouncing it wrong, but that's how I've heard it in my life. I should have zoomed in a little bit quicker when I screen grab, or a little bit better when I screen grab this. Let me do that one more time. There we go. Okay, that should be a lot more readable. My apologies for the delay there. All right. So if z is r cosine theta plus I sine theta in the exact same way we've been writing everything so far, and n is a positive integer, then z to the n, here I'll rewrite this a little bit cleaner next to it, a little bit bigger. Z to the n is equal to r to the n plus cosine n theta plus I sine n theta. I'll put those in parentheses just to make everything very clear. Okay, so if z is r cosine theta plus I sine theta, rewriting this in case it isn't visible well to you in that light text, we've got this nice thing right here. So notice that if z is, say, an nth root of some complex number w, right, or omega, I don't know, I'll probably keep saying omega if I write w. If z is an nth root of omega, where, let's write it like this. Let's write it like this. So where we'll write it like this just to make everything easy, where omega is given by r cosine. We'll move on and imagine that we didn't just use the thetas and the r's for z. So r cosine theta plus I sine theta, all that of course in parentheses, and let's just write z as, I don't know, rho cosine phi plus I sine phi. I don't know. There we go. Then z to the n, by the formula we had before, will be rho to the n cosine n phi plus I sine n phi. So that's from de Moivre's formula. And what we have to have now is the following. Hence, we have to have rho to the n equal to r, and n phi we'll have to have equal to theta. And in reality, what we have to have it equal to is not just theta, but theta plus some multiple of pi, right? K 2 pi, something like that, 2k pi, however you want to write it. Let's write 2k pi instead of pi 2k, whatever we had before. That is bringing this n over. There we go. We've kind of figured out what we need to do. Oh, hey, look at that. These guys are just real numbers, right? Why is this not going there? So this means that rho is going to be the nth root of r. Oh, and phi is just theta plus 2k pi over n, right? Okay. So this is really what we just discovered by looking at all of the spinning things around. The nth root of r is just from these dilating factors, right? Because we keep multiplying by, n copies of the same thing. So we're going to stretch it by the same factor every time. So hence, if we multiply nth root of r by itself n times, we'll get nth root of r to the n, which is just r. So we'll get the right length. We just have to adjust using the nth root. And this is all real numbers right here, so there's nothing special going on. Another way you could write this if you want is that if omega is r cosine theta plus I sine theta, then the nth roots of omega are, or I'll even write that, just, I don't want to write it like that. The nth roots of omega are the following. They are just given by z equals, and what is this r going to be for omega? Well, that's just that's just the modulus of omega. I'll write it like this: modulus of omega, cosine of arg omega plus 2k pi over n plus I sine arg omega plus 2k pi over n, and all of this should be in a big old parenthesis right there. The nth roots of omega here are just these guys, and we can just write it all in terms of omega, and this is for k. I don't want to write equal to here, but I will. People like to do this. 0, 1, 2, ... all the way up to n minus 1. And notice once we get to n, it would be 2 times n right there, right? We'd just be adding enough. We just circle back to what we got at 0, right? Okay, so basically this is like saying, if you're looking at the old planes examples that we were doing before, or the unit circle examples, just to get rid of the messiness that might come from considering something that's not on the circle. Let me make the circle here just to make our lives very easy and nice. So if we're looking at something on the unit circle, let's look at, say, like the fourth roots of 1, right? It'd be this, there, there, and there. Okay, so we'd have, well, the modulus here will be, of course, 1 since we're on the circle. And then we'd get the argument, which is 0, right, of 1, right? So arg, if 1 is omega, then arg omega is 0 since there's no angle up from the real axis, right? It's on the real axis. And then we'll go 1k further, so it'll be 2 pi over 4. Oh, hey, that's pi over 2 right up to here. Then we go another pi over 2 from there. Then we go another one, and then we go another one. Hey, look at that. So we just go here to here to here to here. So if it's 1, then the fourth roots are I, minus 1, and minus I. How about that? So we found all the fourth roots of 1. We didn't even have to really even go through and do this calculation, because you can always just think of splitting up the pi nicely. Now, if we didn't have, say, something on the circle, if instead we were on the unit circle, if we were instead doing something more interesting, you would have to take into account the stretching factor that comes from having a non-unit modulus. But we don't have to worry about that for easy examples like this. And all you really have to think about is the spiraling outwards or spiraling inwards. And so you just either have to start smaller or start bigger and spiral up to it, or start smaller and spiral down to it, that kind of thing. Anyways, we're at 6:52 or 5:52 your time back in Wyoming. I don't want to go on too long. We'll do a whole lot more with all this stuff next time and get a lot of examples in, but this is the basic idea of what's going on. We'll use this a lot. And I think that's all we got for the day. If anyone is in the chat and wants to ask any questions, please chime in now and we can answer any. All right, doesn't look like anyone is saying anything in the chat. Doesn't have any questions. If you got any questions, just shoot me an email. I'm here to help. And yeah, hope you guys have an awesome. Oh, you gotta wait in the chat. All right, I will wait. Oh, you can ask it too in the chat if you want. It doesn't make any difference. Whatever's easiest. Okay, yeah. If you want to send an email, that's all good. I can do LaTeX in the email, so nice typesetting. Well, I don't think that you can do that in Twitch. Yeah, it is definitely hard to type math in a chat box. All right, yeah. So if you want to shoot an email, anyone else have any questions? Just shoot me an email, and I will see you all next week. Good stuff. Bye.